Everybody knows about the rich oil fields underneath the waters of the North Sea, out there. But what's less well known is that in any oil field, including those of the North Sea, something like half, perhaps more of the oil gets left behind in the rocks. And the future of the oil industry depends on recovering a higher proportion of the oil held in each reservoir. Now, in order to do that, oil geologists have to find out all they can about reservoir rocks and how oil is held in them. Of course, they can't actually visit the reservoirs, and in fact, all you ever see of the rocks in an oil field is cores. Cores like this one, taken from widely spaced drill holes. Now, what we can do is to give you a feel for the sorts of problems that oil geologists face by looking at recent sediments. Many beaches would make excellent reservoirs. The constant movement of the sediment by the sea results in well-sorted and rounded grains with high porosity and permeability. Wind-blown sands can also make good reservoirs. The string of sand dunes behind this beach extends for several kilometers, and if buried, could hold a great deal of oil. But not all sediments are so well sorted or so continuous. This shingle spit is at the southern end of the sand ridge. This stuff's pretty poorly sorted, but it doesn't take much imagination to see that an oil geologist encountering it in a borehole would regard it as pretty promising reservoir material. And in fact, here's a core of just such a rock. Only this one happens to be a couple of 100 million years old. Now then, we mustn't think of sediments as being indefinitely continuous sheets or layers. This sticky mud is, for all practical purposes, impermeable. And there are mud flats stretching off away to the south of me here. Here, the mud's banked up against the shingle. So we've got a very abrupt lateral change from shingle to mud, from permeable to impermeable. And changes in the type of sediment that's been deposited are often called facies changes or facies changes. And here, of course, the facies change, is very sudden, very obvious. But in real reservoirs, the changes of porosity and permeability can be much more subtle and much more gradual. And of course, the oil geologist can't walk the reservoirs in the way that we walk these sediments. He won't have drill holes a couple of meters apart. He may only have them a couple of kilometers apart. And so, in order to enhance the recovery of oil from reservoirs, geologists need to know all they can about the way fluids move through rocks. They need to know about lateral and vertical changes of facies. And finally, to apply their understanding to real reservoirs, the geologists need lots and lots of cores. In Britain, cores have remained in the hands of the companies that drilled them. But here at Calgary, in Western Canada, cores are kept on a very different basis. In the early days of the Canadian oil industry, recoveries were often very low, and there was a growing demand for more oil field data and for easier access to it. The Calgary Core Store houses thousands of cores, all available for public examination. This bank of data enables geologists to reconsider earlier work and to reinterpret the distribution of facies in existing fields. One such study was made by Gulf Oil's Jim Dolph.
We're lucky here in Alberta, having many oil fields that require additional study so that we can get more oil out of them by enhanced recovery methods. My interests led me to a field in northwestern Alberta, 200 kilometers northwest of Edmonton, named Goose River. I have before me a map, a more detailed map of this area. This is on a scale of 1 to 500,000. For scale, this lake is 9 kilometers in length. A combination of geological intuition and some seismics led to discovery of a light brown member reef in this area in 1955. This reef is approximately 10 to 12 kilometers in length. Following that discovery and using more geological intuition, other reefs were discovered along this trend. And following that, a reef over here, another reef, crescent-shaped here. Still later, a reef in that position, another here, and another here. These reefs formed on a competent platform consisting of calcareous mud. The platform outline is like this. It relates, of course, to the reef development. So we have platform from here over to a position here, moving around like this. Here we have an embayment in which no platform is present. The particular reef I'm going to be discussing is called Goose River. It's in this position, the oil being present in the northeast up-dip portion of the reef and the water in the down-dip portion. The dip is approximately 2 degrees to the southwest. On this dark brown platform, the reefs grew, and I have an example of the dark brown platform here. It's non-porous, no oil could occur in it, but it is a competent platform. I also have examples of the reef, the light brown reef, that contains the oil which developed on the platform. This is composed of a debris consisting of massive stromatoporoids. Stromatoporoids are organisms very much like corals. In this case, this one looks very much like a cabbage head. There's some porosity within this individual. There's also porosity between the rubble grains that comprise a matrix between this stromatoporoid and that one. This entire assemblage of reefs was subsequently covered by shales of a younger Devonian age, which formed the cap rock and kept the oil trapped in the reefs. All of this information is provided by the wells themselves. Seismics is very little use in this part of the world because there is only a very low velocity contrast between the porous light brown reef and the enclosing and overlying shale. Gulf had a block of land west of the original discovery, which is located on this map. The scale on this map is 1.6 kilometers to each corner of these squares. Gulf drilled its first exploratory well here in 1955. We found 50 meters of light brown reef, but there was very little porosity in it, so we didn't get too interested at that time. A year or two later, a competitor drilled a well in this position. They also found roughly 50 meters of light brown reef with poor porosity, but they obtained a shoal of oil on the drill stem test. So we knew a reef edge existed somewhere up dip and northeast of these wells. So we stepped out in this direction, and we drilled here and found no reef. At the same time, another well was drilled here, and also it found no reef. So we knew, therefore, that the reef edge lay between these wells and these wells. So we moved back to the southwest, and in this position, at the 10-4 well, we drilled a discovery in 1963. Found again 50 meters of light brown reef, but with good porosity, and the test flowed 800 barrels of oil a day, which absolutely delighted us. Subsequent to that, we drilled this area with our competitors and outlined the reef, which I shall sketch now. Now we have the light brown buildup with oil in it in the up dip position. In the down dip position, we have water. The oil-water interface is located like that. Oil production amounted to 6,500 barrels a day by 1970. Now all of this production is by conventional means. Dr. Norman Wardlaw is going to talk about oil production by conventional means and by other means.
Opening a bottle of champagne may seem like an unlikely way to begin talking about an oil reservoir, but in fact there are a number of similarities. The oil in a reservoir is always under pressure and always contains a certain amount of dissolved gas. In fact, quite commonly the oil is saturated or nearly saturated with gas. And when a borehole penetrates the reservoir, the pressure is released, the gas escapes from the oil and drives the oil into the wellbore, sometimes with spectacular results forming gushers. Although the results may be spectacular, they're usually short-lived, as they were in the case of the bottle of champagne, and result in very little production of the oil in the reservoir, never more than about 10 or 15%. And here we see the level has fallen just a little bit, perhaps 10%, below the starting point. This process we call solution gas drive, and it's an important mechanism of primary recovery, but the bottle of champagne will also serve to illustrate another process. In some oil reservoirs, the oil is not only saturated with gas, but there's an excess of gas in the system which occurs as a gas cap overlying the oil, as we see here in our champagne bottle with gas overlying liquid. If a well is completed in the oil part of the column and pressure is released at the surface, the gas cap expands, driving the oil into the well bore and producing at the surface. And this process is a good deal more efficient than the solution gas drive, and in the end may result in the recovery of something like 20 or 30% of the initial oil in place. Following primary recovery, it is possible to inject water into the system in a water flood operation. Now we have an injection well where water is pumped in and displaces the oil in a piston-like fashion, driving the oil towards a production well. This water flood process we can illustrate in some glass micromodels. In this experiment, we're going to illustrate secondary recovery or water flooding. We have here a glass cell which has etched into it a pore system which simulates the pore system in a reservoir rock. And on this side of the equipment, we've got water which is leading into this glass cell and can be thought of as a water injection well. In the model itself, we've got oil and water as it would be in a reservoir, and coming out of this side, we've got a production well, and we've stained the oil blue so that it shows up quite conspicuously. We're going to switch on the pump now for the beginning of water flood, which is the beginning of secondary recovery. And it takes a moment for the water to begin entering the model. And the oil, which is colored blue, is being broken up into isolated blobs, which become bypassed by the advancing water. Here we can see a domain of oil which is almost disconnected. It's just attached by a thin filament to the rest of the oil body, and there we see that that little connection has broken and an isolated blob of oil has formed. That is going to be then part of the residual oil which is left behind at the end of water flood. Well, here we are near the end of secondary recovery. No more oil can be recovered in this particular regime. The residual oil in the reservoir now has to be produced by tertiary recovery. And we can illustrate this by, first of all, increasing the flow rate. If we increase the flow rate quite substantially, we see that the isolated residual blobs of oil start to move. First of all, the larger blobs are broken up into smaller blobs, and as we increase the rate a little bit more, there are more and more blobs which are beginning to be swept out of the system. But in real reservoirs, there's a limit to how much we can increase the pressure and increase the flow rate. So in this final phase of tertiary recovery, we have to go to other means. And one of the things that we can do is to introduce detergents. And we can now see the water with detergent entering the model, and as it does so, the surface tension between the water and the oil is lowered, and the larger blobs begin to move, and you can see these being broken up into smaller blobs. The smaller blobs are moving along in the flowing water stream, and what we see is that there's something less than 10% of the original oil that's now remaining in the reservoir. And we can compare that with the 70% of residual oil which existed at the end of water flood.
Now, adding such detergents to a reservoir is obviously effective, but they're extremely expensive and can only be economic if injected into the right part of the reservoir. And that's where the geologist and his Fassy's model re-enters the scene. Goose River illustrates the potential of such techniques. Production began in 1963 at about 800 barrels per day and increased as more wells were completed, up to a peak in 1972. With only primary and water flood methods, the production began to decline, and it was expected that an economic limit would be reached in 2015. Jim Dolph's study enabled an enhanced recovery program to commence. It's estimated now that production will be maintained through the end of the 20th century, with a sharp decline at about the same time as conventional production would have declined. The difference is the total amount of oil produced, an extra 33%, or some 20 million barrels, by enhanced recovery. That extra oil was recovered by re-examining old cores and gaining a better understanding of the facies relationships between the boreholes by studying a present-day reef in the Bahamas. Although 350 million years separate Goose River from the Bahama banks, similar processes operated to produce both reef systems, and observations made here enabled Jim Dolph to produce a model detailed enough to allow for the use of expensive enhanced recovery fluids.
This is a plastic panel model of the Goose River oil pool. It's built up by successive panels connecting the wells. We originally thought that this reservoir was one single reservoir unit with all wells connecting quite equally one to another. But our detailed study has enabled us to break the reef up into two principal elements. One is a reef on the flank, colored green, a corresponding reef on the down dip flank indicated green and blue, and an interior lagoon colored yellow. Now there's not just one reservoir element here, there are in fact 5. In most cases, each of these drains separately. Here's a good example of a lagoon rock. You'll note that the porosity now is very, very small and isolated. This isolated porosity means that the permeability or the horizontal connection of the pores is very poor, and in some cases there's none at all. In the basic center of the model, there's a lot of yellow indicating lagoon. When you look around the outside, you'll see a large amount of dark green. That indicates the reef flank. When you look around that side, you'll see a fair amount of dark green and some dark blue. That indicates well built up reef around that flank. And when you see a thing like this, if you're a geologist, you suddenly get a little brainwave and say, by golly, that's an atoll, which is exactly what it is. And it fits what we've seen in the field. Here's the fringing reef around the outside of the atoll, and there's a lagoon in the center. So obviously, when we inject fluids, they're going to move very, very rapidly in this direction around the outside of the atoll, but they're not going to move with any speed through the lagoon. So when we plan our injection programs, we'll take this into consideration.
Jim Dolph's success in sorting out the complex relationships between the areas of the reef with different permeabilities was based on data from old cores. It paved the way for the successful use of expensive liquids to reduce viscosity and surface tension. A small but growing percentage of oil is being recovered by the use of such liquids. In some parts of the world, though, the reservoirs are more accessible.
Remember Goose River? These are the same rocks that we saw there in the subsurface in core. Same age, Devonian, same facies with these fragments of shells. And here's a tabular stromatoporoid. Pretty porous and permeable rock. What we've done, though, is we've come east from the basin about 400 kilometers here to the edge of the Great Devonian Basin in Alberta, to where the rocks come right to the surface. This rock doesn't contain any oil now, even though it is porous and permeable. But what we think happened is that the vast majority of the oil generated down there in the subsurface has migrated up dip and laterally and passed through these strata and been trapped just above me here in one of the great oil fields of the world, the Athabasca oil sands. Just around the corner up here, and we'll go have a look at it.
The total area of the deposit is about the same as that of Wales. The estimated reserves of oil are approximately the same as in the whole of the Middle East. The oil sands are part of the Lower Cretaceous McMurray Formation, which is about 50 meters thick and lies unconformably on the Devonian limestones.
This then is a natural exposure of the McMurray Formation. The sands themselves are quartz-rich, very fine-grained to fine-grained, moderately well-sorted, really an excellent reservoir with porosity and permeability that's 2 or 3 times what commonly it is in a conventional reservoir. The sands were deposited in what we interpret as a large channel system. Evidence such as these crossbeds, which you see here, with the foreset laminae dipping off there towards the left, are indicative of flow in the bottoms of these channels along big bed forms migrating downstream under conditions of current that allowed the sand to be deposited but kept the silt and clay moving and in suspension so that it resulted in a very clean and well-sorted reservoir. The evidence such as this, and the evidence higher up in the formation from burrows such as we see here, gives us this idea then of a very large channel system, perhaps source as far south as Arizona and New Mexico, emptying into the sea just to the north of here. Well, the oil, of course, is saturating the sands here. What does that oil really look like? Here it is. The bitumen is an extremely stubborn, heavy, viscous crude oil. It's immobile at reservoir temperature, and indeed, it's only on hot days such as this that the heat from the sun is enough to allow the oil to bleed down off the surface, such as we see here. In the sand, of course, the oil is hosted between the quartz grains, just as it would be in any sand reservoir. But one of the really remarkable features of the oil sands is that you can pull it apart with your bare hands. It has virtually no cement. There you see it. It has high porosity and permeability. The quartz grains are sheathed with a little film of water, very thin film, and then the bitumen resides out in the center of the pore.
Local Indians using the waterways in this region used to waterproof their canoes and boats with the help of this sticky material. Early in the 20th century, attempts were begun to exploit the resource commercially. A variety of methods was tried to separate the oil from the sand. None of them was commercially successful, although they all managed to produce some oil. Today, the extraction of oil sands takes place in these massive mines. This is one of the world's largest mines of any sort. Enormous draglines scoop out hundreds of tons of the soft material and leave it in long rows to be moved again by bucket wheel excavators. These ship-sized machines deliver the oil sand onto conveyors for passage to the processing works. This is not, however, an oil refinery. Here, the sand is tumbled in large hot drums. Stones, pebbles and sand are removed, leaving the bitumen, which is treated to produce a synthetic crude oil, ready for piping to refineries in the south. This process has a very high recovery rate, a good deal better than recovery from most underground oil fields. The short to medium-term future of the petroleum industry depends on higher recoveries from existing fields. And that, like so many other things, depends on a good understanding of the geology.